Hello friends, welcome back to my YouTube channel. Today I will discuss one numerical based on simple distillation. So this is 45th part of my discussion on distillation, and this would be the third video on simple distillation. Let me tell you, these are additional videos. I have already made videos on simple distillation, but I thought I should make some additional videos where you will learn how to calculate XW by using Rayleigh's equation. So in my previous video, that is part number 44, I discussed a numerical where I told you how to calculate XW graphically. And today I will be discussing another numerical. This would be fifth numerical on simple distillation. And in this, we will be using the analytical solution of the integral in the Rayleigh's equation for finding out XW. The analytical solution of Rayleigh's equation for finding out XW, mole fraction of the more volatile component in the bottom product. So we will learn how you can find XW using the analytical solution. I have made one video on the analytical solution of Rayleigh's equation. I'm giving link to that video in the description section. Okay, to begin with, let us understand the numerical statement. You have a liquid solution containing 50 mole percent of N-heptane and 50 mole percent of N-octane. It is subjected to a differential distillation at atmospheric pressure. 60% of the original liquid solution gets distilled in the process. Compute the composition of distillate and the residue. And N-heptane is the more volatile component in this case. Plus, the average relative volatility for the system is 2.16. So, I am discussing the same numerical which I had discussed in my previous video, where I told you how to calculate XW graphically. And in that numerical, the equilibrium data, VLE data, vapor liquid equilibrium data was provided. Now in this case, instead of, in this particular numerical, instead of the VLE data, we have the average relative volatility. The average relative volatility for the system is given to us. And this value or this relative volatility is considered to be constant. Then and then only we can use the analytical solution of Rayleigh's equation. So this is a constant relative volatility, and we are going to use the analytical solution, the Rayleigh's equation, for getting XW. So you have a liquid solution that is containing 50 mole percent of N-heptane and 50 mole percent of N-octane. This is subjected to a differential distillation. Differential distillation means that the other name of differential distillation is simple distillation, or the other name of simple distillation is differential distillation. It is subjected to a differential distillation at atmospheric pressure. 60% of the original liquid solution gets distilled in the process, and we are supposed to compute the composition of the distillate and the residue, that is XD and XW, and they are telling that N-heptane is the more volatile component. So we know which one is the more volatile component, and the average value of the average relative volatility for the system of N-heptane and N-octane, it is given to us, it is 2.16. So first of all, we will collect the given data. So the components involved, there are two components, N-heptane N-octane. Out of this two, N-heptane is the more volatile component. And then the feed solution, it is a liquid solution of N-heptane and N-octane. N-heptane being the more volatile component, I am going to denote it by capital A, and the other component, that is N-octane, I am going to denote it by B. The feed solution is containing 50 mole % of N-heptane in it. That means in this case XF is 0.5. XF stands for the mole fraction of the more volatile component in the feed. We have percentage mole of the more volatile component. It is 50%. And if you divide it with 100, you are going to get the mole fraction. So that's why XF is 0.5. So what is given to us in the numerical statement? It is 50% mole of A. And that's why XF, if it is converted to fractions, XF would be 0.5. Then differential distillation it is used, that is simple distillation is used, and in this process 60% of the feed solution is distilled. So 60% of the original feed solution is distilled. That means the distillate obtained is 60% of the feed solution. Then average relative volatility is given to us. It is 2.16. I am going to denote it as alpha AB average. It is 2.16. And then what are we supposed to find? What to find? The composition of the distillate, that is XD, and the bottom product, that is XW. So based on the information that is given to us, we are going to find these two quantities. First, we will find XW by using the analytical solution of the Rayleigh's equation. And then once you get XW, using that value, we are going to find out XD. Okay, so let us solve the numerical. We are going to start with a basis. What is the reason for that? The reason is we don't know the quantity of feed. Amount of feed is not known to us. So we are going to use a basis of 100 kilomole. F is 100 kilomole. So with this basis, we are going to do the remaining calculations. First, we have to calculate DNW. So for that, we will use this information which is provided to us. Since 60% of the original feed solution is distilled, you can express this mathematically in this way. D is equal to 0.6 F. That is, the quantity of distillate obtained is 60% of the quantity of feed. And 60% is 0.6. In fractions, it is 0.6. So F we have assumed, or we have chosen the basis of 100 kilomole, and you can easily calculate D. So therefore D will be equal to 0.6 into 100, that is D is equal to 60 kilomoles. And then we will be using total material balance, steady state total material balance to get W. So steady state material balance is F is equal to D plus W. So this will be 100 is equal to 60 plus W. So that gives us W as 100 minus 60. That is W is equal to 40 kilomole. So in this way, we get distillate and then we get the bottom product, amount of distillate, amount of bottom product. Then let us use the material balance for E. FXF, that is equal to DXD plus W into XW. And in this case, F is 100, XF is 0.5, D is 60, it's 60 into XD, plus W is 40 into XW. So that is 100 into 0.5 is 50, that is equal to 60 XD, plus 40 into XW is 40 XW. So you get one equation in which there are two unknowns, XD and XW. So you cannot solve as it is. We have to get either one of these two quantities, XD or XW. And our approach is we are going to get XW by using Rayleigh's equation. So that's why the next task is calculation of XW. So XW is calculated by using the Rayleigh's equation. What is Rayleigh's equation? Ln of f by w is equal to integration from xw to xf dx upon y minus x. And we are going to use the analytical solution. Again, I have made one video where I have derived the analytical, or I have told you how to get the analytical solution for Rayleigh's equation. I am giving link to that video in the description section. In this discussion, I am going to use the equation directly. Okay, so we are calculating XW. For that, we are using the Rayleigh's equation. Ln of f by w is equal to integration from xw to xf dx upon y minus x. Since alpha AB average is constant, so you can go for, or you can use the analytical solution of the Rayleigh's equation. I am directly taking the solution. I have derived it. I am giving link to that video. So the equation is ln of xf into f divided by xw into w, that is equal to alpha AB average into ln of f into 1 minus xf divided by w into 1 minus xw. So f is known to us, it is 100 kilomole, that is the basis. Xf is 0.5, w we obtain for f to be 100 kilomole, it is 40 kilomole. Alpha AB average is given to us, it is 2.16. Now let us use these values in the equation. So you have ln of 0.5 into 100 divided by xw into 40, that is equal to 2.16 into ln of 100 into 1 minus 0.5 divided by 40 into 1 minus xw. So I have used all the known values in the equation. So that is ln of 50 by 40 xw, that is equal to 2.16 into ln of, this will be 50 divided by 40 into 1 minus xw. So I have simplified it. So that is ln of 1.25 divided by xw, that is equal to 2.16 into ln of 1.25. So 40 by 50, 50 by 40 is 1.25. So 1.25 divided by 1 minus xw, that is ln of 1.25 divided by xw, that is equal to ln of 1.25 divided by 1 minus xw raised to 2.16. So here I have used the logarithmic identity. What is that? M into log ln of n is ln of n raised to m. So I have used the logarithmic identity to get this equation. Okay, so previously we got this equation. Ln of 1.25 divided by xw, that is equal to ln of 1.25 divided by 1 minus xw raised to 2.16. So in the next step, I'll take anti-logarithm on both the sides. So this will be 1 by 25 divided by xw, that is equal to 1.25 divided by 1 minus xw raised to 2.16. Now in the next step, what I will do, I will separate the power on the right hand side. So before I tell you about the step, let me tell you. So over here I am doing this 1.25 raised to 2.16 divided by 1 minus xw raised to 2.16. And then this 1.25 raised to 2.16 I am taking on this side. I am taking xw to the other side. And so therefore it will be xw upon 1 minus xw raised to 2.16. So on this side, 1.25 divided by 1.25 raised to 2.16 is 0.77. So I'll rearrange it and then I'm writing this step. So xw divided by 1 minus xw raised to 2.16, that is equal to 0.77. That is xw is equal to 0.77 into 1 minus xw raised to 2.16. So again, I will write it in a different form. Xw minus 0.77 into 1 minus xw raised to 2.16, that is equal to 0. So this is of the form f of xw is equal to 0, where f of xw is the function that we have obtained. What is that? It is xw minus 0.77 into 1 minus xw raised to 2.16. Okay. Now, in order to get the value of xw, the thing is clear. One thing is clear. You need to solve this to get the value of xw. So, you have to do it by trial and error, because on one side you have xw or an simple xw. On the other side you have xw in a function that is raised to some power. So, it would be difficult to get the value of xw by using simple mathematics. You need to solve it by trial and error. You can use your calculator to solve this equation to get the value of xw, or what I am going to tell you, I'll tell you how to use a root finding method, numerical technique, to get the value of xw. And over here I am going to use Newton-Raphson method. The task is to solve this equation, that is, get the value of xw that will make this function 0. So, for this I am going to use the Newton-Raphson method. So, to get xw, f of xw needs to be solved, and f of xw will be solved. In this case, I am going to solve it by using the Newton-Raphson method. Let me erase this so that there is no confusion. So, we are going to solve f of w by using we are going to solve f of xw by using the Newton-Raphson method. And what is the formula for Newton-Raphson method? The new xw n plus 1, that is new value for xw, that is equal to xw n, old value of xw, minus f of xw evaluated at xw n, the function evaluated at xw, old value of x, divided by derivative of the function that is evaluated at old value of x, that is xw n. So, f of xw is, we have that equation. We need to get its derivative so that we can use this formula. Now, f of xw is xw minus 0.77 into 1 minus xw raised to 2.16. Now, the derivative f dash of xw will be 1 minus 0.77 into 2.16 into 1 minus hw raised to 2.16 minus 1 into minus 1. So, we are getting derivative of this. So, derivative of xw with respect to xw is 1. The function on the right hand side, you have this function 1 minus xw raised to 2.16. And for this, you can use the formula for derivative of x raised to n. What is the derivative of x raised to n? This is n into x raised to n minus 1. So, if there is a function of x in place of x, which is the case in this case, in place of x you have 1 minus xw, and we are going to differentiate it with respect to xw. So, in that case it will be, you can use the formula for x raised to n, and the only thing is you will have to multiply with the derivative of the function. So, in this case it will be, for this particular, I'll write over here 1 minus xw raised to 2.16. So, according to the formula it will be 2.16 into 1 minus xw raised to 2.16 minus 1. And since xw is in a function, you'll have to multiply with the derivative of this function, and derivative of this function with respect to xw. So, the derivative in this case is minus 1. So, I have used this formula over here. So, f dash of xw, that is equal to 1 minus 0.77 into 2.16 into 1 minus xw raised to 2.16 minus 1 into derivative of the term, derivative of the function. Derivative of the function is minus 1. So, if you simplify it, you will get f dash of xw is equal to 1 plus and the product 0.77 into 2.16 is 1.66. This minus and this minus, it will become plus. So f dash of xw is equal to 1 plus 1.66 into 1 minus xw raised to 1.16. So this is the value of the derivative, or this is the derivative of the function. So now you know the derivative, you know the function. Now you can use the formula for Newton-Raphson method. So let us do that. Let us use that. Okay, so we are going to use the Newton-Raphson method. The formula is xwn plus 1 is equal to xwn minus f of xwn divided by f dash of xwn. F of xw is xw minus 0.77 into 1 minus xw raised to 2.16. F dash of xw is 1 plus 1.66 into 1 point xw raised to 1.16. We got this in the previous step. So first iteration. So the first iteration for doing the first iteration, we need to start with assuming value of xw. And in this case, what I will do, I will assume the first value, or for first iteration, let me first write the formula. For first iteration, the Newton-Raphson formula will be written as in this way. xw1 is equal to xwo minus f of xwo divided by f dash of xwo. So first assumption is, there is an initial case, that is x0. xwo, it is 0. So I am going to use the first assumption. It is up to you. You can use one thing is xw will be between 0 and 1. Minimum value will be 0 and maximum value will be 1. So you have to choose a value that will be lying between 0 and 1 or 0 and 1. So I'm using xw0 as 0. So if I do that, I will have to evaluate the function at this value. So f of xw0 will be xw0 minus 0.77 into 1 minus xw0 raised to 2.16. So that is f of xw0 is 0 minus 0.77 into 1 minus 0 raised to 2.16. That is f of xw0 is minus 0.77. Then I will also have to calculate f dash of xw0. So it will be 1 plus 1.66 into 1 minus xw0 raised to 1.16. That is f dash xw0 is equal to 1 plus 1.66 into 1 minus 0 raised to 1.16. That is f dash of xw0 is 2.66. Now I can use the Newton-Raphson formula to get xw1. So xw1 will be xw0 minus f of xw0 divided by f dash of xw0. That is xw1 is equal to 0 minus 0.77 divided by 2.66. That gives me xw as 0 plus 0.289. That is xw1 is 0.29. So 0.29 can be written as 0.29. So in this way, first iteration is completed. I started with an old value for xw as 0, and I have got a new value as xw1. And what is that value? xw1 is 0.29. Okay, now let us go for the second iteration. For second iteration, the formula for Newton-Raphson method will be written as xw2 is equal to xw1 minus f of xw1 divided by f dash of xw1. xw1 is 0.29, which we got in the first iteration. So therefore f of xw1 will be xw1 minus 0.77 into 1 minus xw1 raised to 2.16. So that is f of xw1 is equal to 0.29 minus 0.77 into 1 minus 0.29 raised to 2.16. So that gives us fw1 as minus 0.079. Then let us get f dash xw1. So this is here 1 plus 1.66 raised into 1 minus xw1 raised to 1.16. That is f dash of xw1 is equal to 1 plus 1.66 into 1 minus 0.29 raised to 1.16. So that gives us f dash of xw1 as 2.12. Now by using the formula, let us get xw2. So xw2 is equal to xw1 minus f of xw1 divided by f dash of xw1. So that is XW2 is equal to 0.29 minus 0.79 divided by 2.12. So that gives us XW2 as 0.29 plus 0.0371. That is XW2 comes out to be 0.33. So I have followed the same steps to get other values for XW. So I'm showing that in this particular table. So for different values of these are the old values. These are the values of the function at old values. These are values of the derivative of the function at old values, and these are new values of XW. So for you must have understood when we used XW to be 0, we got minus 0.77 as the function, then 2.66 as the derivative of the function, and new value was 0.29. And then in the second step, we got the function at XW1, it was 0.08, that is minus 0.079 is approximately, it is nothing but 0.08 minus 0.08. The derivative of the function is 2.12 and new value of XW is 0.33. So when these steps are repeated, when you go on doing the iterations, you'll come to know that you are getting a constant value for X, and that is the end of the solution. And this is the root of the equation, the value of the XW, the value of XW that is required. So in this case, we get XW as 0.33. Okay, so we got XW. Now let us get XT. So for that, we are going to use material balance for A, which was obtained earlier. You must be remembering the equation that we got was 50 is equal to 60 XD plus 40 XW. XW we got it as 0.33. You must remember, if you check my previous video where I have solved I have got XW graphically, you'll come to know that the same value was obtained over there. And here also we are getting the same value. XW is 0.33. So 50 is equal to 60 into XD plus 40 into 0.33. That is 50 is equal to 60 XD plus 13.2. 40 into 0.33 is 13.2. Therefore 60 XD is equal to 50 minus 13.2. So this 13.2 is brought on this side, and you have 60 XD is equal to 36.8. That is XD is equal to 36.8 divided by 60, and that gives us XD as 0.61. So in this way, we got XW as 0.33 and XD as 0.61. So with this, I end my discussion for this particular numerical. Here, you must have learned how to use the analytical solution for Rayleigh's equation for getting XW. Again, you need to use a trial and error method for getting the value of XW. You can use your calculator, or you can use any root finding method to get the value of XW. So thanks for watching my video. I hope you have learned something. If you have any doubts, you please mention them in the comment section. Do subscribe to my channel. Tell your friends to subscribe to it. And I'm sure you'll join me in my next video on another topic in chemical engineering. For now, have a nice day. Bye bye.